Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to discuss about the nominal flexural strength for doubly symmetric compact I-shaped members. So one thing that we need to understand that we are only dealing with doubly symmetric section and compact I shapes. So in case of compact I shapes, so we will have only these two type of failures because of flexural loading, yielding of the section or the lateral torsional buckling of the beam. So there will be no local instability, mean there will not be any flange local buckling or web local buckling because the section is a compact section. So the nominal flexural strength of a compact section will be governed by the yielding of the section or by the lateral torsional buckling of the section. So in case of lateral torsional buckling, we can have three cases: either the buckling is elastic, inelastic, or there is no buckling. So the first one is the nominal capacity corresponding to the yielding. So in case of yielding, the nominal capacity can be calculated as Mn is equal to Mp and it is equal to Fy times Zx. Mean the section is yielding completely and we are reaching up to the plastic moment capacity of the section. This is only possible when there is no lateral torsional buckling and there is no local instability. Okay, next is lateral torsional buckling. So if LB unbraced length is less than LP, so in that case there will be no lateral torsional buckling and the capacity will be equal to plastic moment capacity, and we can calculate it by Zx time Fy. Zx is the plastic section modulus and Fy is the yield strength of the steel. So this case will be similar to that of the yielding. So the next case is inelastic buckling. So if LB unbraced length is greater than LP but less than LR, so this LP and LR are the limiting values. So I will define these factors LP and LR in the next slide. So if LB is greater than LP and less than LR, so in that case there will be inelastic lateral torsional buckling of the member. So in that case the section may develop yielding at only some points and the nominal capacity of the beam will be given by this one. So in case of inelastic lateral torsional buckling, so there will be lateral torsional buckling, but before that lateral torsional buckling, the section can yield at some points. So in that case, the nominal capacity can be calculated by using this expression. So before going through the derivation of this expression and how this expression is actually derived, so I would like to proceed further, which is when LB is greater than LR, if the unspotted length is less than LR, this limiting value, so in that case, there will be elastic lateral torsional buckling. And if there is a elastic lateral torsional buckling, then the flexural capacity, nominal flexural capacity will be equal to FCR times Sx. Now we will see what are these LP, LR and this FCR. So here LP is the limiting laterally unbraced length for full plastic bending moment capacity. So if unbraced length is less than LP or equal to LP, then we will have full plastic bending moment capacity given by Zx time Fy. So this is the limiting value which actually define the point or the unbraced length for which we can get the full plastic bending moment capacity. And LR is the limiting laterally unspored length for inelastic torsional buckling. So if the unbraced length LB is equal to LR, so in that case we will have inelastic lateral torsional buckling, but if unbraced length is beyond this LR value, so we will have elastic lateral torsional buckling. So these two values are actually limiting value, the dividing lines between no buckling, elastic buckling and inelastic buckling. So this FCR is compression flange critical buckling stress. So FCR is equal to CB times pi square E over LB over RT whole square multiplied by this factor. So this can be approximated, we can ignore this factor and we will get the approximate value of FCR. So here if we see in this calculation of FCR, which is the critical buckling stress of the compression flange, so we have this CB which is lateral torsional buckling modification factor that will be defined in the coming video. And LB is the unbraced length, RTS is the radius of gyration of the compression flange, and this JC is the torsional constant, C is a constant or a factor which is different for compact section and which is different for doubly symmetric or unsymmetric sections. Sx is the section modulus, elastic sectional modulus. H naught is the distance between the center to center distance between the flanges, compression and tension flange. So here we can see how we can calculate this factor to calculate the FCR value. So this RT S square is equal to IYCW over Sx square root. So if we substitute the value of CW for doubly symmetric section, so we will get this expression. So we can write it over like this: RTS is equal to square root IY H naught over 2 times Sx. So IY is the second moment of area about the y-axis. H naught is the distance between the flange centroids, mean D minus TF by 2, and this Sx is the elastic section modulus. We can also approximate this RTS value, which is radius of gyration of the compression flange, plus 1/6 of the web for doubly symmetric I section. So we will assume that this flange and 1/6 of the web. So we will consider this as a T member, and then we can calculate the RTS value. We will calculate its IY about this y-axis and then divided by the area, so we can get this RTS value. So this is given by this equation. So we can substitute the values. BF mean the width of flange, H depth of flange, and thickness of H is the depth of web, T is the thickness of web, and this BF and TF are the width and thickness of flange. So by substituting these values, we can calculate the RTS value, which is the approximate radius of gyration for the compression flange. Similarly, J is the torsional constant for the section, so we can calculate this by using this expression 1 over 3 BT cube. So here we will distribute into 3 figures, mean like this: 1, 2 and 3. So for each figure we will calculate this factor 1 by 3 BT cube and then sum up these values. So in that way we can calculate the JC value, or otherwise we can get the JC value from the properties table given in the LRFD manual. So here C is a factor which is equal to 1 for doubly symmetric I shape. So here we are only dealing with the doubly symmetric compact I shape, so we can directly consider this value equal to 1. Otherwise we can check the value of C from the AISC design manual. Okay, here this diagram shows the nominal strength of the beam corresponding to the laterally unbraced length. So if laterally unbraced length is less than LP, the limiting value LP, so in that case the capacity will be equal to MP. And if the unbraced length is more than LP but less than LR, so we will have inelastic behavior, and its nominal capacity can be calculated by linear interpolation or by intersecting this linear line. So for example, for this LB value, so we will intersect this line, and corresponding to that we can calculate the moment value. And if the unbraced length is more than this LR, so we will have elastic behavior, we will have elastic lateral torsional buckling, and its capacity can be calculated by FCR times Sx. So if we see in this graph, so corresponding to LR, we have the moment capacity which is equal to MR, and it is given by 0.7 Fy Sx divided by 10 raised to the power 6. So here we can say LR and MR, this point. And here if the unbraced length is equal to LP, so we will have the capacity, corresponding capacity equal to MP. So here we will have the point LP and MP. If the unbraced length is in between LP and LR, so in that case we can interpolate the value in between these 2 points by linearly joining these 2 points. So for example, here we have the point which is equal to LB and MN. So now we can write the slope by using these two equations and by using these two equations. So if it is a straight line, so the slope written by these 2 points and then by using these 2 points, so the slope because of these 2 points and these 2 points, so it will be same. So we can write that LP minus LR divided by MP minus MR is equal to LB minus LP over Mn minus MP. And after simplifying this expression, we will get the equation that is for the inelastic behavior, the nominal capacity for the inelastic behavior that we have seen in the previous slide. So by using this expression or by simplifying this expression, we can get the Mn value.